So today's topic is going to be was going to have a happier ending than last time. Last time the conclusion was yikes and unlucky, but that's the nature of distributed systems. I'm going to continue with the process model that I used last time. The events filtered through some transformation, apply some state feedback loop, and then the outputs come out the top. But this time I'm going to analyze it in the context of testability, and I'm always concerned about, well, okay, I'm doing multiple different approaches to prove informally that this is a general model of computation for both distributed systems and message passing systems in general. And I'm concerned that I'm constructing a circular argument saying that this is the good way to do things because these good properties come out of it because it's the good way to do things. So just be aware of the potential of a circular argument forming, so just pay attention to that. Hopefully it's not completely circular. So the approach I'm taking, what was taking last time was looking at how must a distributed system be, and hence that was the decent way to program one. Today I'm going to take the approach of what must a testable system be, and the conclusion is the same as last time. That's the general structure you end up with, which makes sense because it's a general structure, but it has a bunch of subtleties. So the first thing I want to do is just look at the functionality hierarchy of a computer program. There's degrees to which a computer program works. It either doesn't work or it works perfectly. And then you have methods for achieving the higher degrees of workingness, as it were. So the first, at the bottom, you have your compiler and your language mechanisms. You have things like static types instead of dynamic types, so you can compare strings and integer, and it gives you not a number, which is technically true, but not particularly useful. And then you have formal verification systems like Christopher talked about yesterday with Spark and so on. This also exists in multiple programming languages, and type systems vary in degrees of how good they are at helping you out. So you can more easily create a correct program with good type systems and verification and so on. Then, of course, eventually the type system doesn't help you anymore and you need to test it during development. So the base level is a unit test where we're testing a single function of code. And then you can do integration tests where you're integrating multiple functions or multiple modules, looking at the interactions, how these things actually work. And usually you would want to do this with some kind of real-world data, so that you're not testing it with just fake values, because you can always say, this is fake data, does it work with fake data? Yes, of course, because I've constructed it to work with fake data, so hopefully you have some real-world data in there as well. Then I'm running out of slide space here, so I'm going to use the right-hand side. Then you can do testing while the program is running to make sure that it keeps working while it's running. So we have the generic error handling stuff, error return values, exceptions, you all know this stuff. Then you have acceptance tests, which not just handle one type of error, but hopefully multiple classes of, or at least one class of errors. So you look at, has the data remained, does it still have integrity? For example, our GPS system reports our position, but compared to last time, are we suddenly traveling at 700 miles per hour? In that case, we can say that this system is no longer functioning as expected, but it is functioning as accepted because there's nothing wrong with the values, it just doesn't make sense. And then you can combine these. Well, if you can detect all manner of errors, all manner of not reasonable data, then you can do things like, well, we can handle all kinds of, can detect all kinds of errors. Let's see if we can handle all kinds of errors. And the thing that captures most kinds of errors would be restarting the entire program. As long as you make sure you restarted with, if it crashed because it had bad data, and then you restarted with the same bad data, that's obviously not going to work very well, so you'll have to have some kind of fallbacks and not just a straight restart. So that's the topic for exercise 6. Not so much looking at the acceptance test part, but at least the process pair part. And then finally at the top, we can, instead of saying that our computation is correct and we've detected as many errors as we could during development and we've detected all the errors we can during runtime, we're like, there's still things we haven't captured. So we're just going to do it multiple times, but preferably on multiple hardware platforms, running multiple different or slightly different algorithms developed by multiple teams of people. And that's how you end up with, please scroll wheel, continue working.
Well, we are having one or two little problems at the moment. It won't be too long before we're with tonight's episode of
Inversion program. There we go. I'll have to edit that out of the video. Yeah. So at the top is this thing called inversion programming. Have you touched on that yet? No? Okay, so this is coming later in CITES courses. So eventually, well, things that you already know about are type systems. Hopefully unit test, I mean, you've tested your code, you've had a function and you're like, does this work? So you've done, at least informally done unit testing. You've done generic error handling. You haven't done acceptance tests or process pairs. That's going to be later, and inversion programming is also going to come later. So today's focus is on the unit test and integration test side of things, and then again next week, process pairs. So let's look at what actually makes code testable. Well, let's look at some very boring basic code. Yep. Is this code testable? Yes. Okay, this is so trivial that it might not even need testing, but that's kind of the point. So let's make it less testable by introducing some amount of complexity. Does anyone disagree that the example 2 is less testable than example 1? Okay, well, let's see if we can make this even worse. I mean, it's very easy to make things worse. It's hard to make things better. So it's amazing how much of a mess you can make with such a small amount of lines of code. So I want you to think about what exactly is it that makes this such a pain in the ass to test. There should be like a static int c at the top of example 3 as well. It didn't happen, but. So what are the interaction points that make things more or less testable? Wow, okay, we're getting some interaction here. I was just going to skip over, but yeah.
Well, if you have static variables, you will have state.
If you have static variables, you will have state. Yes, and state captures the time varyingness. Yeah, exactly. So let's look at the hard part first, because identifying the things that made it hard is easier than identifying bad things is easier than identifying good things. So the first problem we had was that, well, the first problem was state. That's the second problem. Well, the first problem is that we don't know where these values come from. We have these static variables that were global. Global variables, yeah, you don't know where they are. You don't know who modifies them. So that's the biggest problem. You don't know who and when they are modified. So they could be the internal values, they preserve state, which is complicated. The external values preserve state, and they also have this interaction with potentially an unknown amount of other units. So we have these implicit dependencies. If you look at the code, we have these implicit dependencies where we just take one of these variables, our parameters. The other two are implicitly, we depend on them, but we don't know where they are. They're not made explicit. But if we do this properly, we have these explicit parameters. We have both A, B, and C, which are all the things that we are using as parameters. And then we have the statefulness. We don't know what's saved for next time. So in order to test some specific scenario, we need to call the functions in some specific order, which is a pain. We've been across this ordering in time problem before. This is nothing new. So in the end, really the big thing that makes testing hard is interaction with other components. Isolated things are easy to test. Distributed things, well, not necessarily distributed across an unreliable system, but even distributed across a reliable system is a pain in the ass. So let's look at what makes testing easy. Well, functions that don't have any implicit dependencies, or rather no dependencies at all. They just have straight inputs and outputs, and these functions are called pure functions. This is just not just me talking, this is just the way it's defined. These are called pure functions. No, only inputs and outputs, do not transform the outside world in any way, and are not transformed by the outside world in any way. So I guess they're electromagnetically compatible functions, if you were to think of it that way. I'm not sure if this is completely the correct word. Disassociating the functions with the data. Well, if you have a struct or a class and it has some private data and then it has some public functions, then the public functions can interface with the private data. So there's a connection between the data and the function. That is implicit because they're not parameters to the function. So we want to make sure that all the connections between the function and the data are made completely explicit, and the only way to do that is parameters and return values. So really, when we are testing the code with data. We pass the data to the code and get data back. We are not testing the code and the data. The data is just there. It's just a value. It's just immutable. It doesn't need testing. It's the function that needs testing. So, if interactions were the hard part, we want to make sure that when we're testing one thing, we want it to, well, the one thing we are testing will in the real world, when it's done, interact with other components. Because having a system of completely disassociated components isn't a system. It's just a bunch of disassociated components. It's like a library. So we need to connect the components together to create a functioning program. However, the problem was that once you connect them, it becomes inherently untestable. So what do? Well, you want to make sure that these connections are not connected to the real thing, but let's say, pretend what happens if we connect these things to some kind of doubles. We replace them with proxy objects, mock objects, things that aren't the real thing. So instead of, say you have in the elevator project, you have a state machine that executes a set of orders, and then you have some kind of order management system that makes sure that these are distributed and you get them in from the button presses and so on. So these things need to interact. But in order to test the state machine, you don't want to depend on also simultaneously testing the packet loss management of your order handling system. You want to test these two independently of each other, which means that you don't want to get the orders from the network, you want to get the orders from a proxy network, which is no network at all, hopefully. Does this make sense? Limit the amount of interaction by replacing them with not the real thing. So this has a couple of benefits. It gives us isolation, which is what we wanted. It lets us do more testing because you don't need to worry about all the interactions. You can focus on one thing at a time, which makes it easier to test, lets you do more testing. And there are also tool systems and type systems that let you do a lot of automated stuff here. We're not going to cover that today, but often this happens. But of course, there's a big drawback, which is a lot more obvious than these subtle benefits. We're not testing with the real thing anymore. We're not testing with real data. We're testing with fake data that we've smuggled in between. We have two interacting components, and we've smuggled in some fake barrier between them where we put in our fake values. So instead of saying, hey, or testing our order management system, instead of saying, hey, state machine, execute the order, we're saying, hey, pretend state machine, you are always immediately executing the order and saying that it's completed. So we have a fake state machine that immediately completes the order regardless. Okay, that lets us test our order management system, get a new order, we confirm it, we send it to our state machine, which immediately completes it, and then we get to check the completion result as well. Okay, but what if the state machine doesn't actually work? So we have the fake values, it doesn't look too hot. These objects the proxies may go out of date, especially if we're fixing bugs. We assume that the thing that we are mocking out is mocking out sensibly, but we update the real one without updating the mock, and it's a pain in the ass. So, conclusion, let's just test the whole damn thing anyway. Because we can't get the isolation that we wanted, so whatever, let's just test the whole thing. Does anyone see a problem with testing the whole thing? Yeah, of course, it's combinatorial explosion time. Because now you have a set of paths, a set of conditionals, the different paths your code can take depending on the input data in one module, but you also have a set of paths in the other module, and then you have all the interactions which depend on the paths you take through each of the modules. The amount of space you need to test to make sure that the entire system works is so large that it's basically infeasible. Which is why there are people who say that integration tests are a scam because of this. And I'm inclined to agree, at least to some extent. So really, the problem we have is the boundaries between modules. We need to interact with other modules because that's how our program works, but we don't want to interact with other modules because it makes testing impossible. Okay, well, we have the interface of the other module. Cool. We want to make sure that when we're interacting with the interface of other modules, we're not interacting with fake modules, we're interacting with the real stuff. And we don't want to connect anything. We don't want statefulness. We don't want to do destructive things in other modules, because statefulness means that, well, testing one thing and then testing the same thing afterwards will have different results because it preserves states. So really, the only thing that we can have, the interaction between modules cannot be function calls, because function calls can preserve states. So the interaction between modules must just be data, just values. Okay, interesting. Data is immutable. Data doesn't change unless it is changed by a function. So really, if you want to create a testable system that has lots of components, the way the components must interact is by passing data to the other components, not by invoking behavior in other components. So we're not calling functions from other modules, we're passing data to other modules. Do you now start to see the difference between like an object-oriented structure and a message-passing structure? Object-oriented structure, you invoke behavior in the other objects, which means that you are responsible for how the other object behaves. Message-passing structure, you are just giving it a value and you are no longer responsible for how it behaves because it is its own process. So inherently, message-passing systems are more testable than object-oriented systems just based on this alone, which is cool. However, we still have one more problem. We just had immutable data. We wanted functions that don't modify anything because functions that don't modify anything are easy to test. So we have data that doesn't change and functions that don't change data. Really, we just can't build a system like this because now we have a system where nothing can change and nothing can do the changing. So we need to introduce the concept of changing things, mutation, statefulness, time in general. Ordering in time was a big problem. That's the one we need to fix. But we want to be very careful about it so we don't introduce global variables immediately. So really the two questions we have are, we have some set of data. We need to know where this data should live. And we have some set of things that are allowed to modify data. Not all the things, because we want most things to remain testable, but some things must remain fundamentally untestable because they change things. And the question is, how much of that should we have and where should it be? So, the thing that made things testable was by lifting things into parameters, not having implicit states, not having global variables, not having internal states. So we lifted everything into the parameters of the functions and the return values of the functions. So the question is, how much do we lift and where do we lift it? So we have some amount of hierarchy here. So at the top of the hierarchy, everything is parameters. Oh yeah, I just said that. Cool. Yes, and yeah, of course, the parameters that we lifted out were the program state. We went from global variable program state to the state now lives in the parameters. And interestingly, by doing that, by lifting the parameters into, or lifting the state into the parameters of the function, since it's no longer internal to the objects, it is now the responsibility of the one who calls the function to maintain that piece of state. So we're lifting the states up into the call hierarchy all the way until you reach main. So that's at the top of the hierarchy. The top of the hierarchy is all our program state is in main, just the top level function. One God object. This is really just a database. So people who are making Java apps for web servers in the early 90s, they were actually just doing this. You have a database that stores all your state, and then you have a bunch of functions that manipulate it. Of course, if you put all your data in one place, you need to understand how all the data all the combinations of valid data that could potentially exist in your entire program. So that's combinatorial explosion time. This just imposes a cognitive overload. There's no way in hell you're going to be able to do this. So let's see what happens if we go the other extreme. Let's see. We spread our data as much as possible. I'm not quite sure how you would achieve this, but let's put one Boolean in each process or something like that. So let's see what happens. Well, the problem with that is sometimes you need to modify multiple pieces of data at once. For example, the elevator starts moving. Yes, it starts moving, that's one piece of data. And then let's say, it arrives at a floor, which means that we have stopped moving, but we have also arrived at a new floor. So we're changing both the movingness of the elevator and the flooriness of the elevator, and potentially also clearing some orders. So we're changing the ordered amountiness of the elevator as well. So there's 3 pieces of data that we're modifying at once. So if we're spreading this all over, well, then we need to reach into the other things that store data and transform them somehow. And we're back to the invoking behavior into other modules. So this isn't working, because now we have one piece of code trying to modify multiple pieces of data, and one piece of data that is being modified by multiple pieces of code. So we're back to the untestable land. So more parameterization seems like the thing we want to lean towards, but we can't have the ultimate amount of parameterization because it makes our program, well, one giant monolith of huge amounts of data which we need to hold in our head at one time. So let's see if we can find where does that split go? Where is the middle ground? Because as usual, there's a middle ground. It's the same thing with the distributed systems from last week. You can't maintain complete consistency, but you don't want no consistency, so there's a middle ground. So it's the same thing happening here as well. So the middle ground that I've found the most success with in both my own programming and looking at what other students are doing is that you divide, your program has some amount of state. These are all the variables that exist in your program. Then you divide that data based on what is the least amount of data that you need to be able to modify at one time. You don't need to modify all the data, but there are some groupings of data that you need to modify at once. So again, same thing from last time. Data is useful because it's being mutated. Process is useful because it's stateful. So we want to find the least amount of data that we modify at once. So this gives us that piece of data is only modified by one thing, but that one thing can modify multiple pieces of data. So we don't have both the many-to-many relationship. We've collapsed it into a one-to-many relationship, or hopefully just a one-to-a-few if we're optimal about it. So this is better. So the data that we get out, the data that is separated by who is writing to that data, is the data that becomes the state of one stateful process in a message passing system. This is the top level thing that you do when you're designing your project if you're writing it in any message passing language. Find what data must exist in your program, find out what is the grouping of data that must exist in order to modify the largest amount of grouping you can get, where you don't group it in such a way that you need to reach into other modules to modify multiple things at once. Does that make sense? I hope that makes sense. Divide the data based on who is writing to it, not who is reading from it. You can always get a copy. Divided by who is writing to it. And then you create one process for each of these. And then you connect them together with channels and message queues and whatever. So really, the things we're looking for by dividing into a writer are good properties. These are kind of vague, but you've probably heard of these concepts in some amount of code quality concepts. One module responsible for modifying things that belong to that kind of responsibility. It's a bit vague. one module is uniquely responsible for owning that piece of data and thereby uniquely responsible for modifying it. Really, what we're just looking for are things that belong together, which seems a bit vague, but the belonging togetherness, if you want the non-vague version, it's grouped by who is modifying it. Apparently, my next slide is this one. So, what did we have? Well, we grouped our data based on who is modifying what. That data becomes the state at the bottom right of our circular process. And it gets a bunch of inputs from other modules. And these inputs are just values, they're not function calls. And it produces a bunch of outputs at the top, which are also just values, not function calls. And then we have these transformation functions, which join together the event that you receive and the state that you have, and generate a new state and a new output. And what's cool about this is that the algorithms that determine what the next state is and what the output should be don't actually have to modify anything at all. They just tell you what the next step is. Finding out what the next step is and actually performing the next step can be separated. That's the cool part. Which means that all the algorithmic complexity can be made in such a way that it is trivially testable, based on how large or complex your algorithm is, of course. But it is at least testable, and then the modifications that you need to perform, writing back to the state and writing to the output, that's the stateful stuff, which is hard to test because it invokes interactions with other modules. So that's cool. What we've accomplished now is that all algorithmic complexity in your system is now testable. So that was a combined approach where we need to have interaction with states, but we want as much as possible to be testable. So we have some core here, which are these pure functions determining the outputs and next state from the events and current state. These are pure functions. These have lots of paths, lots of algorithm, hard to create perhaps, hard to program, but easy to test. So these are perfect for unit testing. And then we have this shell on the outside, which actually performs these modifications. That's the stateful process. And in there, we have very few paths, maybe no paths at all, because the path is determined by the algorithm. But we have lots of dependencies, because this stateful process interacts with other stateful processes. So these are good for integration testing. So we know that the internals of each process works, and we can now connect all the processes together. As long as we explore the paths for all the connections, well, we have n squared plus n squared instead of n to the power of 4 amounts of interactions. So we don't have a combinatorial complete explosion anymore. Integration testing is always going to be much harder than unit testing, but at least now it's within the realm of being manageable, which is good. The thing that we need to, since it's manageable, it turns out that you might even not need to test it, because you can just look at the code and say, yeah, this is correct, hopefully. We'll see. The thing that's important to remember here, though, is that the boundaries between the core functions are just values. They're just inputs and outputs. And the boundaries between the shells are also just values, not function calls. So really, now let's look at the internals of that transformation step again, and we can see if we can divide these into a shell-core divide. So we have some shell functions that transform states. So we have some small amount of logic here, switching on the events and switching on the internals of the states. But all the algorithmic complexity for figuring out what the next state should be, given our current state and event, are pure functions. And that's the thing that's hard to create and hard to test. So I'm going to go through that process with the state machine now afterwards. I don't know what the time is. 46 ago. The thing worth noting here is the nesting order or amount on the shell side is not that important. If you switch event first or switch state first or only switch event and not state, as long as the depth of your conditions aren't more than 3, you want to stay 2 or below, hopefully. 3 or below. Then you'll achieve something good. Just be pragmatic here. These are not absolute rules. It's not like you have to have only one if or no ifs in your state transformation application shell function. These are not rules. They're more like guidelines, as a certain pirate says. So let's look back at what the approach is for creating a message passing program. This is like the summary slide for section 1. First, find all the inputs and outputs of your system, the real-world inputs and outputs of your system. Shouldn't be too hard. Let's read the specification type stuff. Then you need to find what data needs to remain persistent in your program, which is what is the state of your program. And this state must obviously come from the real world somewhere, which is usually the inputs and outputs. So explicitly from an input, we need to remember what the input was, or implicitly from the output, we need to remember what output we did set previously. And of course, there's one that I didn't write down here, but that's time. Time has a tendency to just progress whether you like it or not. So that's also a viable input to your system. It's not a viable output, though. You can't output time, can you? I don't think so. Input, at least. Then you need to find out which of these inputs actually modify the data, or modify which data, then split the data based on who is modifying what. That's the segmenting our entire state into lots of smaller pieces of state that are manageable. And then we split these into individual processes. So one piece of state per process. And then we wire these together with queues or channels or other message passing mechanisms. And then the only thing we send are values. We don't send pointers, we don't send references, we don't send duplicates. Well, we can send duplicates of values as long as they are straight duplicates. We don't send access to the same piece of data from multiple places, because now you have a shared variable, which is what you don't want to have. And of course, the final step, which must always be a final step, is you need to iterate, because you're never going to get it right the first time. There's some amount of love for a waterfall development model in some industries, which can work and cannot work. But let's put it this way. You don't have time to do a waterfall approach on this project, at least, because you need to think very clearly and for a very long amount of time to get a perfect design the first time. It's much easier to try something, see what works, pay attention to what you're doing, of course. Like, there must be an observation step in the feedback loop. Having a feedback where you just apply new outputs without observing what you have done isn't useful. So pay attention to what you're doing. Look at it in the context, in this context, preferably, because it seems to work. And then iterate on your design until it lands on something usable.